So many pop-ups. Gets me confused. Okay, so welcome back. So this is going to be module 8, and I have 92 slides to go through in 2 hours. So you'll have an hour at the end of the class to discuss about your project. While we start this class, my section, you can see some comments in e-learning as well, just like PM name. So you can just go to e-learning and look at the proposal. I have put some comments there. That's for my section. Okay. Okay. So in this module, we're going to look at assembly language and extension to the previous module. So this is an extension to go for more of the advanced things in this assembly language. Okay. Okay, the first one we're going to see is a conditional execution. So if you notice that in the previous module, Associate Professor Munim has mentioned about this CC. That is a conditional code that you can attach to the instructions. Okay, and with this conditional code, the instruction will either execute or not execute depending on the condition. Okay. So the first one we're going to look here is the branch. Okay, so the branch is one of the ways for you to actually modify the direction of your program. So in a flowchart, you'll probably look at it as the following. You will have this diamond shape, which means a decision, and the decision can go in a couple of different ways. Okay, so you can go to a yes or a no. Okay, so this is actually the change of the path or the direction of your program. Okay, so this is what we call decision making. Instead of your code running linearly, that is line by line, what could happen here is that we can have a jump. So from here, we jump to a different portion of our code, or we can jump backwards, okay, depending on your behavior. So jumping around in the code is actually changing the behavior or changing the direction of your code. Okay, so the important concept here is that branching, regardless of what branch we have here, which we are going to discuss in a while, regardless of the branching, the main point here is that our program actually executes linearly in the first place. Okay, it executes linearly means line by line. And the way to know what is the next operation that you need to do is actually based on your program counter. Okay, so your program counter is one of those registers that we have in our CPU. So the program counter, if you remember the definition, it is a register which contains the address of the next instruction to be fetched. Okay, not executed, to be fetched. So actually the program counter is telling the CPU what is the next instruction to be fetched, and then later executed and so on, and then the next instruction and the next instruction and the next instruction and so on. Okay, so the key register here is program counter. Before I continue, have you taken advanced computer architecture? Have you taken this? Anyone? Some of you?
Yes, please semester.
Okay, so if you're taking, you realize there's PC there as well, right? Program counter, right? So the program counter is actually responsible to tell you where your program is going to fetch the next instruction. So if I change this thing, if I change the program counter, then I effectively change the next instruction that I'm going to fetch. In other words, I'm changing the direction of my program. So the point here is that these instructions that you see here basically indirectly affect the program counter. They change the program counter in order for you to change the direction of your program. Okay, so in terms of a flowchart, it's simply a diamond shape like this that tells you whether your algorithm is going this way or your algorithm is going this way. Okay, so that's a diamond in terms of a flowchart. In terms of our code, it's like jumping around in the code. Jumping means the program counter is changing. Okay, changing, incrementing or decrementing depending on what you have. Okay, so okay, just give me just 1 second, please. Okay, I'm back. Okay, so sorry for the bit interruption. So we have what we call 2 different kinds of branches. So one is called the unconditional, and the other one is a conditional branch. So unconditional means that there is no condition for it to branch to that place. So let me give you an example. If you have a main function in C programming, okay, since we are doing C program, right? And somewhere in the C programming, you are calling, let's say, add, a subroutine called add or function called add, okay? Okay, so this sub function here, so it's incompletely written, but you have this add function here. So your program will run, and when it sees this add, it's going to jump to this function. And when you're finished from this function, you're going to return to the next line here. Okay, so there's no condition for you to take add or not take add. You will always take add when you arrive to this add. Okay, so that's what we call unconditional. There is no condition tied to it. The moment you see it, you're just going to jump, and the moment you finish, you're going to jump back. Okay, sort of like that. So there's no condition to it, so we call that unconditional. Okay, the pen is a bit thin. Is there a way to make it thicker? 3 points. Okay, so what about this conditional? So the conditional is when you have things like if and else. Okay, so if and else is when a condition is met, then you execute this block, otherwise you execute the other block. So there's a condition tied to it, so we call that conditional branch. Okay, okay, so I don't kind of like this, it's too thick, so I think one is okay. Okay, so in order to do this unconditional branch, just like Associate Munim has mentioned in the morning, is just branch. Okay, the branch, and the label to where you want to branch. Okay, to label to, let's say, the branch to a label called exit. Okay, so that's unconditional. There's no condition tied to it. While if you have a condition, then it's going to be something like this: BEQ, branch equal. Okay, branch equal. So it will only branch to the label process if the condition is equal. Okay, and of course the condition equal depends on whoever changes the what we call status flags, and those status flags that we have are actually N, negative, NZ, 0, carry, and overflow. So equal means the two things are the same, which means we're actually looking at the Z flag. Okay, if two things are equal, then it is 0. So we're actually looking at the Z flag. So the branch equal is actually looking at the Z flag. If the Z flag is 0, then this line will jump to the label process. Okay, so that's the key idea here. Now, who sets these things depends on the instruction before it, or could be any instruction before it, whoever that updates the status flags. Okay, it could be one instruction before, could be two instructions before. In other words, whoever updates the flag last time it updated the flag, that is the flag that's going to be used in this branch equal. So we have branch equal, branch if carry clear, branch if less than, branch if greater than, and so on. So these are all what we call the conditional codes. The conditional codes. Okay. Okay, so the purpose of these branches are actually to go forward or go backward in terms of memory address. Okay, so if you have something like that, so you can have yes and no. So yes goes here, no goes here, for example. So you're branching forward, so something like that. If the branch is fulfilled, then it moves to a label forward in time. Forward in address. Okay, or you can have something like this. Okay, going back, looping back upwards, that is jumping backwards. Okay, or in the case of a loop, you have a counter and then you keep on repeating something many times. So it's same like that. So you have a counter, you start with a 3, and then you decrement the counter by 1, it becomes 2, as long as it is greater than 1. So keep on looping this and so on. So so you will use these branches in order to simulate, or in order to implement loops, and also implement if and else, and also implement switch case, also implement do while. So whenever you see loops, whenever you see decision making like if and else, switch case, it will always come back to this branch. Okay, because all of these things are actually changing the direction of your program. Okay, so these are the flags. We have looked at this in, I think, chapter 1 or 2, if I'm not mistaken. So these are the important flags. We have the negative flag. When the two things, when you compare, you get a negative. So the comparison is very straightforward. Okay, so we can just assume this. The comparison is like this. So this is not Barisan National. Okay, it just happened to be a scale. So you have A and B. Okay, so when you do comparison, that is using a compare operation. Actually, you're doing subtraction. Okay, subtraction. So the thing is that we want to find whether these two things are the same or greater than and so on. So if A and B are the same, so A minus B will be 0. Okay, so that will affect the Z flag. If A is smaller than B, okay, which means it's lighter, okay, and this is heavier, okay, then A minus B, you're going to get a negative. If A is greater than B, then it's not going to be negative, it's not going to be 0. And if it's a signed number and so on, then you will see the carry, you see the overflow flag as well. Okay, so these are the things that you see in order to determine whether it is equal, whether it is greater than, greater or equal, less than, and so on. So the key concept here is simply subtraction. Okay, the other key concept here is that the difference is I don't care. I just care A minus B. I just care whether it is 0 or is it positive, is it negative, and so on. The difference I don't really care. So if I say A is 100 and B is 20, or A is 100,000 and B is 20, in either case, A is greater than B, regardless of the difference. Okay, regardless of the difference. So the difference here is just 80. The difference here is like 999,980, a very large number. Really doesn't matter. What matters is just the sign. Okay, the sign. Okay, so that's another key point here. That operations that we use to do comparison, they only look at the sign, which is reflected in terms of the flags, but the result of the subtraction is always what we call remove. Not remove. It's always ignored, or is always discarded. Okay, we don't really care the difference in terms of the value. What we care is just the sign. Okay, okay. So we have that 32-bit instruction. So when we have this conditional code in our instruction, the top 4 bits are actually reserved for this conditional code if you're using it. For example, if I want to use an equal, for example, add equal, so the add opcode will be somewhere around here for which register and destination register, if you have a shifts and so on. But the equal, the conditional code is actually represented by the top 4 bits here. Okay, so if I say add equal, which means add only when it is equal, then the conditional code in terms of the binary representation of the instruction will be 0000. Okay, so in terms of the machine code, it will be 000. But in terms of the effect, it's actually looking at whether that operation will be executed when z equals to 1 or not. So when z equals to 1 means the z flag is triggered. So the z flag, this is a flag, the z flag is triggered, which is 1, which means effectively means the answer is 0. So this will only happen when whatever the previous result is 0. So this instruction will get executed. And again, not equal, which means z is not 0. That makes sense, right? So if z is not 0, it could be positive, could be negative, which means it's not equal. Okay, in terms of the machine code, it will be 0001, and you can see other things like minus. Okay, branch if minus, we are looking at the negative flag, and so on. Okay, so you may have to think a bit more. For example, why greater or equal, you're looking at this. So a bit need to look at a bit on the digital logic. Why you have to look at n equals to v, which means it's greater or equal. But nevertheless, the concept here is that we are looking at the CPSR, what we call the flags, the flags, the NZCV flags, to determine whether the decision is taken or not. And the condition code is represented by the 4 bits here. And the other important thing here is that you don't have to remember these codes. Okay, this is just to educate you actually how it's actually implemented in the machine code, but you don't remember this. Okay, this one, of course, you may want to think about it. Okay, when you say overflow set, so overflow set, overflow clear, overflow clear. So a bit of a basic understanding should have that. Okay, so let's look at the C code here and the equivalent assembly code here. Okay, so if a equals to 5, then call the function fn10. Call the function and pass a value 10. So if you see, if a equals to 5, so imagine a is in R0. Okay, so we compare, the operation we're using is compare. So it's actually subtraction, but it discards the result. Okay, so a minus 5. If it is equal, then the z flag will become 1. And the next instruction moves the value 10 to R0. Okay, if it is equal, that is equal, then it calls a branch and link if equal to function. Okay, so a couple of things here which you may not understand. First of all is what is branch and link. Okay, why are we moving 10 into R0? Okay, so these are a few things you may not be clear at this moment, but will become clearer later. But for a quick one, whenever we call a function, okay, a function, let's say this is a C function, and then you have the parameters that you can send to the function, right? Okay, so the first parameter is always sent through R0, the second parameter is sent through R1, the third parameter is sent to R2, and the fourth parameter is sent through R3. So I want to send the value 10 to the function, so I'm moving the 10 to R0 prior to calling the function. So that's the convention, and we're going to look at that in this chapter. Okay, what about this branch and link? Okay, so we have the regular branch. We also have this branch and link. So the purpose of branch and link is this. So a quick one. So you have these lines of code. Okay, and then let's say this is the function f here somewhere in your memory, and this is your main function here. And you're jumping from here, this point, you're jumping to the function. That is a branch. That is a branch. Okay, and then you're going to continue executing the function n. So let me fix this. This is function n. Okay, and when you end the function here, you're going to have a return. Okay, you're going to have a return, and when you return, you're going to return to the next line after this. Obviously, you cannot return to the same line, then you will keep on jumping around, right? You must go to the next line, right? If you jump back, if you return back to the same line, then it's going to be another branch and repeating it, and you're going to stuck in an infinite loop. So obviously, when you finish the function fn, that is this function, when you finish this line, you're going to continue here, the next line. So when you finish this one, you're going to continue here. That makes sense, right? The question here is that what is the address of returning? Okay, the address of returning must be saved. Okay, so when you go here, when you want to come back, you need to keep the address to return. I think there's a story about Red Riding Hood, right? Goes through the jungle, and then she took her bread, right? And then she put the breadcrumbs all along the way, so that when she finishes reaching the destination, when she wants to come back, she will just follow the breadcrumbs, right? But that's a terrible idea, because her breadcrumbs are then eaten by animals, so you will lose your way back, right? There must be a method for you to keep the return address, right? So the branch and link actually takes the return address here, which means this address, and keeps it into another register called link register. Okay, so the specific instruction branch and link tells the machine that I'm going to perform a jump. Please keep the next address in the link register, so that when I want to return, I can pick up that address and return back from where I came. So that's a branch and link. Okay, what about this example? If A double equals to B, means if A equals to B, so we compare the two things. In this case, A is in R1, B is in R2. If this condition is true, then increment A. So if it is equal, increment A, add. If it is not equal, then decrement. So subtract not equal. Okay, so you can see here very compact code in ARM. Okay, you don't have to have branches. It's simply conditional. If the condition is met, you put equal, you do this. If it's not equal, you do the other one. Okay, and you can look at the other ones here. Okay, and maybe I'm going to pick this one. Okay, the reason here is that you can see here is comparing R0. This is assume this is C. Okay, comparing R0, that is C, with A. Okay, compare with an A is a character here. Okay, if it is not equal, which means C is not equals to A, then it's going to compare with B. Okay, and if it is what we call equal now, then R1 becomes 1. So Y becomes 1. So R1 is Y. Why you have this double comparison here? One of it is not equal. The reason here is that this is an OR operation. For OR operation, as long as this is true already, I don't really care about this anymore. Can see that? That's the thing about OR. You can early terminate the OR. Okay, as long as this is true, which is this is 1. Who cares about this? This could be 0. It is still 1. Right, so that's why it tries to compare the first one. If it is not equal, then only compare for the second one. Okay, then you proceed. Otherwise, if this is already equal, this is no longer required. You can straight away compute the equal. Okay, so all can be early terminated. Okay, so that's where the compare instruction comes in. So the compare takes two registers. Okay, and basically it just subtract the two things. okay, updates the CPSR, conditional codes in the status registers, but the result is not stored, is actually discarded. So subtract and compare, they are the same thing, except subtract, the result is kept. Okay, the result kept, but compare, the result is discarded. We don't need the result, we just need to know the sign. Okay, what about this one? This one is the same thing again, but now you're comparing with an immediate value. And the final one is compare negate. This one is actually comparing with the negative of the second operand here. Okay, the negative of this one. So effectively, it becomes add. By the way, should I zoom out a bit? Okay, no, it's right. So because you A minus B, this is compare. Compare negate is A minus the minus of B, which effectively means it's an add operation. Okay. But of course, no result is being kept, only the difference. Okay, so this one is compare with 42. This one is compare with minus 42. Look at the negative. Okay, this is a test. Can I read this note here? I put a note here actually. Can I read the note? Okay, so the test operation actually performs an AND operation. Okay, so test for a particular bit here. So I want to test a bit number 0, which has a value of 1, right? So bit number 0 is actually 2 to the power 0, which is 1, right? So I'm actually checking for bit number 0. So the test instruction is actually AND instruction. Okay, it's actually an AND instruction without keeping the result. The other one we have is a test equal. Okay, so there's a note here. It's actually performing exclusive OR. Okay, it's actually performing exclusive OR. It's actually looking at whether these two things are similar or not by performing exclusive OR. Okay, so you can have a look at these notes later. How did I get to know this? You can simply look at the standard manual. It's written there that this actually performs exclusive OR. Okay, now what about this one? This one is the same thing, and now you're comparing with 42. So this one is R0 minus 42, and the result goes into R1. So we have the AND result here, but for these things, there's no AND result, only update the flags. Okay. Okay, so let's have a look at some basic ARM code. Okay, so this is an if statement, decision making. So we have that if statement, right? So we have something like that. So if x is greater than 0, then x is x minus 1. Okay, so a decrement of x. So the first one is 10 goes into x, so move 10 into x, so R3 holds the x. There's a comparison here. So compare R3 with 0, that is our immediate value. Branch if less or equal. Okay, so if it is less or equal, then you will go here. If it is greater, then you will go here. This is greater than, this is less and equal, which means outside the if. So if it's greater than, you will do this. If it's less than equal, you are going to jump out. You're going to jump out. So if it's less than equal, you're going to jump above this. Otherwise, you're going to do the subtraction. Okay. Moving forward, so in this case, now we have two conditions. We have two blocks. So we have this one, we have one block here. We have another block here. The previous example was this. We have one block here. The other one just joins at the bottom here. Okay, that was the previous example. This one, now you have the true and false block. Okay, so in the true block, you're going to decrement. Okay, in the false block, you're going to increment. Okay, so let's have a look there. We compare. If it is less or equal, go to else. Okay, let's go to else, and there's a label here where you are going to increment by adding. If it is what we call greater than, then you are going to decrement. This decrement, and of course, there's a mistake in this slide. After your decrement, you have to jump out here. Okay, you have to jump out here. If you don't have the jump, then it will just continue and increment. So there's a bit of mistake there. After the subtraction, you have to have a branch, so you will jump over the increment. Okay, otherwise it will just fall through and also increment, which is incorrect. What about this one? This one is simply a C code saying something like that. Okay, R0 and R1, trying to find the maximum between these two things. If R0 is greater than R1, then the result is R0. Otherwise, the result is R1. It's just taking the max. Let's have a look here. Compare R0 with R1. If it is less or equal, okay, less or equal, which means this block, this is less or equal, sorry, less or equal, okay, then goes to the else, that is move R1 to R2. Otherwise, R0 goes into R2, and then this is the correct one. The branch, you jump over to this one. You cannot continue. So this is the thing I was saying here. You need to have another branch here to jump over, okay? Just like this one, okay? The other option is this one, where we use some conditional codes here. So compare R0 with R1. If it is greater than this one, if it's greater than, then perform this one. This is greater than, so perform this one. If it is less or equal, perform this one. So if it's less or equal, perform this one. Okay. So there's another compact way of writing the same code. And there's another example here. It's same with this one. I'll leave it to you to look at it yourself. These two things are the same. All of these things are the same. Okay. Okay. So just have a look in your free time. The last one. Otherwise, I can't make.
Prof, so the suffix GT and LE, and that means the code will look if the flag is shows value greater than, then only it will do, and then it will ignore the other. That means the first GT and LE are linked together. Only either one can happen. Is that correct?
Yes, correct. But don't say it as linked together. They are separate instructions. Okay, but this instruction will be executed if the condition of this one is greater than. This is actually updating the thing, right? So if this is greater than, then this will get executed, but this instruction will not get executed.
Okay.
So the next one here is that using this is an OR and OR operation, and we have three things to check. Is R1 equals to 1, or R1 equals to 5, or R1 equals to 12, then the result is R1 is 1. Okay, so that is the final result. R1 is 1, so that's pretty straightforward. Okay. But what about the rest? Okay, so that's where you use a test equal. Okay, so if you go back, where is it? Somewhere around here. So test equal actually checks whether the two things are same or not. Okay, so very straightforward. If it is equal to 1, okay, equal to 1, then it will set the flag to 1. If it is not equal to 1, then check is it equal to 5. If it is not equal, then check is it equal to 12. So if any of these is equal, then it's going to set the Z flag to 1, and then finally the move equal will get executed. If it's not equal, then Z will be 0. Then we'll check the next one, not equal to 5, Z will be 0. Then we'll check the next one, is it equal to 12? No, Z will be 0. Then this will not get executed and the program will just continue. Okay. Moving forward, so again, we have a couple of different checks there. Okay. And then goto is like calling a function. Okay. Surprisingly, goto is considered as a bad way of programming, right? But if you look in embedded, you'll find a lot of goto. Somewhere I read somewhere it says that it's one of the simplest way to write your program, okay, to make the code compact, and something goto is just good enough, okay. So don't be surprised to see goto. Goto is like a branch, okay. So in this case, the first one is checking with 0, okay. So if it is equal to 0, then it's going to set the flag to 1, right? But if it is not equal to 0, then check, is it minus? Is it minus? Is it minus? Which means this one. Is it equal? This one. Is it plus? This one, which is not 0, not negative. Okay. So you only check once. And this will update the NZCV. In this case, we are looking at 3 conditions, which is equal. If it's equal, then Z is 1. We are checking whether it's less than. Sorry, cannot fit lah. Okay, here I'm just checking NZCV, okay, the test, and the outcome can only be, sorry lah, why writing not so properly. Okay, so the outcome can only be as follows, the following condition. It could be equal, so in that case Z is 1, and branch equal will occur, the rest will not happen. Or it could be greater. Greater means not negative, not 0. Okay, or it could be less than, which means it's negative but non-zero. So this will the equal will be taken, this will be the plus will be taken, this will be the minus will be taken. So test once and then you branch according to whatever the flag that was set. Okay, and it will go to the appropriate labels as required. Okay, and whatever you do, then you do lah. Okay. Okay, what about this code? This code is simple one-line code. Said this is a pseudocode. This is a pseudocode saying that can I find an absolute of R0? Oh, so in terms of mathematics, is R0 equals to absolute of R0? Okay, so R0 is absolute of R0. So what we're trying to do here is that you try to compare with 0. Okay, try to check whether the number is 0 or not. Okay. So the outcome of test equal could be a few things. When you compare something against 0, you could have a following outcome. One could be that x is equal to 0. That is the first outcome. The second is x is greater than 0. The third one is x is less than 0. Okay, so if the number is equal to 0, there's nothing to do. The absolute of 0 is 0. You have to do nothing. If the number is greater than 0, which means the number is very positive, the absolute of a positive number is the number itself. There's nothing to do. But if the number is less than 0, now we want to do what we call absolute. Okay, so that's why by just doing a test, it will update the NZCV flags, and we only consider the minus condition. So if it is minus, which means if it's this minus, then only 0 minus the number to get the absolute. Okay, so if you have a minus 5, to get the absolute is 0 minus minus 5, you get positive 5. Okay, and you only do this if the number is minus. If the number is 0 or positive, don't do 0 minus, then you'll get a wrong answer. So that's why you have this minus conditional code here. Okay, I'm going a bit slow. I think I'm a bit slow, so I'm going to speed up a bit more. Okay, what about this one? These are all examples only. So in this case, you have this compare, and we have these ASCII numbers. This is all ASCII numbers. Sorry, ASCII characters. Okay, characters. Okay, so it may appear as 0 here, but this is not a 0 number. It's a 0 character. So if you look here, character map. Let's give me a few seconds. Minimize this, and let's say go for Arial, and the number 0, okay, has a ASCII code of 30. Okay, so there's a 30 there. See that 30. So it's a character 30. So just to show you that. Okay, so back to the slides here. Oops. Okay, so we're just trying to compare something with ASCII characters. Okay. So here it's trying to compare, is it less than 0? Because the ASCII character starts from 0 to 9. Okay, and then you have that capital A to Z, and then you have the small a to Z. So if it's less than this character, it's a different character. It's not a number. It's a different thing. Okay, so we just want within this range. Okay, and we just want within this range. Okay, so in this case, we're trying to do here is that we compare R0 with that value. If it is less than, we use this branch if carry clear to other. Okay, to other. Otherwise, it is what we call a digit. Okay, a digit between 0 and 9. So you're trying to compare whether the number falls between 0 and 9. So in other words, in the C code, is it an alpha numeric character? Is it an alpha? The function name is alpha, to check whether it's an alpha or alphanumeric character or not. So by checking, by comparing it with the starting point 0, and by comparing it to the end point here, we want to know whether the number falls within this and that. Why branch if carry clear? So this is something interesting also. So actually, I opened the help here. Where was it? This is not the one. That's the problem. Actually, I opened it. I closed it already. Is it in CSAT? Yeah, I think it's no, not this one. Okay, maybe during the break, I'm going to find you the thing. Okay, it actually explains that. Where is it? This one. I should have put a note here. So actually, when you do the subtraction, if it is less than, the only flag that is not turned on is actually the carry flag. Okay, the only flag that's not turned on when it's less than is the carry flag. So we use the condition carry clear in order to determine whether it is less than or not. So there's a table for that. Actually, I've closed that PDF. Now I have to search back that PDF. Once I do that, I'm going to show you back that one. Okay, so hold that. Okay. Okay, so what about this one? This is a simple switch case. Okay, so in this case, this is a number R0. And based on the number, is it 0 or 1 or 2 or 3, between 0 and n, whatever. Okay, so you're going to go to a different state. Okay, so if you remember, I mentioned to you during C programming that we can use case switch to do state machine. Okay, so again, very straightforward compared to our R0, which is our value that you want to check. If it's equal to 0, then branch equal to, if it's equal to 0, which means state 0, branch equal a branch to state 0, and then state 0 you have some code you want to do. If it's equal to 1, then branch to state 1. So you may have a state machine like that, state 0, state 1, state 2, state 3, and this state machine is implemented in terms of this, let's say, switch case, and this switch case, when you translate to assembly, will look something like this. Okay, you have the value and then you branch accordingly. Okay, of course, there's a remark here. It is kind of slow if n is very large, so maybe there may be a different solution for that. Okay, what about this one? Okay, a quick one again. In this case, we want to jump between this jump table. Okay, so ADR actually gets you the address of that jump table here into register 1. So now we can use register 1 as an address, and then we compare with the value of 3, for example. Okay, is it within this range? Okay, and then we use this 3 to get the offset. Okay, so this will be your base address. R1 will be your base address here. R0 is the value 3. Okay, and this is 2 to the power 2. Okay, this is the number of shifts. Okay, because this one got a word, right? The difference between each is word. So the spacing between each label here is word. Okay, so to get the effective address is actually the base address plus the number of where you want to go. Okay, and then shift it by 2. Okay, or shift it by 4 bytes. Okay, that would be your effective address, and then you go to the effective address and then you pick that one and put into your program counter in order for you to change your direction of your program. Okay, sorry, I'm speeding up, so if you have any questions, you can just ask me. Do while, there's a do while here. Basically, the concept is the same, so just going through the examples very quickly. X equals to 10, so you move the value 10 into some register. So in this case, R3 holds the value of X. And then you do once, then you check for condition. So the condition is after. You can see the condition is after, not before. You don't compare first, you do first. So what you do first? You subtract first. Okay. So here you're subtracting something with something. R3 is your X, right? So X minus 1. And then you perform the comparison. That's a comparison. And if a condition is met where it is greater than, then you say branch if greater to loop. So then it loops up. So this is a do while. So you do first, then you check for condition. Going forward, this is while loop. It's the same thing, except now you do the check before. Okay, you do the check before and then you do the branching later. So a couple of different styles. You can look at this style or you can look at this style. They mean the same. What about for loop? The concept about for loop here is written a bit unformatted here, but probably is trying to show you the 3 different things we have. We have the initialization, the initial value of our counter, that is 10. We have our condition, and then we have our incrementation or the update, right? So in the normal way, we write it this way lah. Semicolon, X bigger than 0, semicolon, X minus minus, and then we have the for loop body. But it is illustrated this way so we can see things separately easily. So X equals to 10, so X equals to 10. X greater than 0, so you must perform a comparison first. Okay, and then is it greater than? If it is greater than 0, then you perform this operation. If it is less or equals to 0, you don't do this. So in this case is an inverse operation. If it is less or equal, you exit. If it is greater than, you proceed. What do you proceed? You proceed with this thing. That is y plus x, so there'll be y plus x. And in the next iteration, you x minus minus, so x minus minus. Okay, so that is the translation of a for loop into the assembly code. More on this thing. This is actually a loop for constant number of times, so 10 times, starting with I0. This is 10, compare with 10. This is increment. Do something, I do not know you're doing what, so whatever you have in the body, do that, and then you keep on branching. If it is greater than 10, then you jump to end. Okay, so that is the style for loop. Again, similar here, but more compact. Okay, what about elements in an array? Okay, so arrays are a bit complicated, so I need to draw a bit. So when you have an array inside your program, normally in C we write like array x, let's say 3 values. Okay, so you're gonna have the 3 values here. Let's say 40, 30, and something like 40, 30, and 0. Okay, this is how you write it in C. So the x here. Okay, so inside memory you're gonna have 40, you're gonna have 30, and you're gonna have 0 as declared here. And each of this data is integer, so it's gonna be 4 bytes of memory. Okay, considering integer to be 4 bytes, 32 bits. Okay, depending on your platform, but for the sake of this class, be it 4 bytes. Okay, the standard size on the ARM chip. Okay. Okay, so the address of the first one, let's say, is 0. This may not be the correct address in the correct data memory, but just to illustrate. And the next one will be at address 4. The next one will be at address 8. Okay. Okay. So this will be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B. Okay. So each of it is consuming 4 bytes of memory. The X here is actually just the memory pointer to the first data. So X is the address of the first data in the memory. Okay, so the second data, okay, let me confuse you. This is index 0, this is index 1, this is index 2. The first data is at index 0, the second data is at index 1, the third data is at index 2. Okay, so confusing you with zeros and 1. Okay, the reason is because C program actually defines a location based on offset. So since X is already pointing to the first data, so the first data is at this location plus an offset of 0. Okay, so it's at index 0. Okay, offset of 0. So that's how we see it. Okay. Although the data is the first data, but it's at offset 0. Now, coming back to this one, so if I want to read the second data or index 1, what it means here is the base address plus 4. That's the location for the next data. And if I want to read this data 0 here, that will be base address plus 8. Okay, so I hope you understand that first. Okay, so coming back to this one, so move 40 to X0. So move 40 to a register first, then use the instruction store for memory operation. Store R0, that is 40. R0 is 40 now. To R4, what is R4? R4 is the base address of X. So I'm storing 40 to address 0. Okay, what about this one? This one is take 30 into a temporary register R0 and store this R0 to the base address plus 4. That would be this location. And what about this one? This one will be load this one from memory, load this from memory, add the two things temporary, and finally write it back to this memory location. So a couple of steps there. So first of all, load at the base address. The base address will have X0 into R1. Next one, base address plus 4, that will be this one, load into R1. Now we have R0 and R1. Now let's add them up. So add R0 in R1 into my temporary register. That would be still R0 in this example. So R1 plus R1 into, sorry, R0 plus R1 into R0. So R0 is my temporary. Now this temporary, write it back to X2. So store R0, that's my temporary, into my base address, which is this one, plus 8, that is X of 2, plus 8. Okay, so I hope you understand the array operation. Okay, so array, whenever you see array, the name, the variable name of the array is just pointing to the base address of that huge array. Okay, I'm just going to go bulldoze through, so not stopping now. So clear elements in an array. So we have that memory just now. and it's A is the base address, and you have a lot of elements. In this case, we have 10 elements, A of 0 until A of 9. Okay, we're going to clear all of them by writing zeros here. So we move a value 0, we get the base address of A. Which one is which one I'm writing? R0. Okay, so this is my clearing value 0. This is also a 0, right? But this is actually my I. Okay, I, because you don't confuse. This 0 is R0. This I is the blue one. Okay, the blue one. How did I know that? Because I see incrementing I. Okay, I'm also not genius, you know. Okay, so I just have to analyze the code a bit. So I'm incrementing R1. That definitely will be my I. So R1 is I, and this is just a value I want to write. So 0 to R0, A is my base address. 0 to R1, R1 is my I. Compare R1 with 10, that is comparison. Make sure you don't repeat more than 10 times. Okay, if it is greater than 10, then finish. If it's less than 10, take R0, which is a value of 0. Okay, store it to R2. What is R2? R2 is my base address of A. Base address of A. R1, what is R1? R1 is my I, so that would be base address of A plus the current index I times 4. Logical shift left times 4 times logical shift left by 2 bits. That is times 4. Okay. In other words, I'm incrementing the address by 4, plus 4, plus 4, plus 4, plus 4, plus 4, plus 4, because apparently A is integer. Not shown here, A is integer. Okay. If it's an unsigned integer 8-bit, then plus 1, plus 1, plus 1. If it's a short value, then plus 2, plus 2, plus 2. If it is a integer, in this case 32 bits, so plus 4, plus 4, plus 4, plus 4. So I'm incrementing the address by plus 4 and writing a 0 there by storing. After that, increment I and loop. Loops without or with compare. Okay, so this is counting up in loop. So in this case, we move a counter, we initialize the counter with 0, and then we increment the counter, and then we check, is it 10 or not? If it is not 10, then loop. If it is 10, then you proceed downwards. How about this one? We start the counter with 10. Then we subtract 1. If it is not equal, okay, what is not equal? Not equal to 0. If it's not equal to 0, then loop. So you can see here, this is much more compact. Okay, so it's much preferred to count down rather than count up. Okay, so countdown is easy to check against 0. We have a special flag for that anyway, the Z flag. So it's easy to detect whether you have reached 0 or not. There's no flag to detect whether it's 10 or not. You have to check for greater than and stuff like that. So easier to count down, more efficient. This is just an example. GCD is greatest common divisor. Okay, GCD. Who cares what's the algorithm? Okay, what's important is the algorithm is given to you. It says that if I not equal to j, as long as I is not equal to j, then is I greater than j? If yes, I equals to I minus j. If I less or equal to j, then j equals to j minus 1. So an algorithm. You don't really need to know what it's actually trying to do, but it's just an algorithm. Okay, so let's translate this to some simplified pseudocode. Greater than means I is greater than j. Less than means I less than j. Not equal means I not equals to j. If greater than means I minus j back into I. If less than means j minus I back into j. If it's not equal, then go to loop. So where did I get this not equal? This one. The main condition. Not equal. As long as you are not equal, repeat this forever. Okay, so that's where you get this not equal. Less than and greater than is obvious. You're checking for greater than or less than. Okay, this is a greater than. This is not less or equal. This is just less than. Because equal already checked here. Okay, so it's not possible to have less and equal. You can have a greater or less. Less and equal will not occur because you had to check for that before. Now, in terms of your assembly, it will be extremely compact. You can see here, extremely compact. We're comparing I and J. This you cannot compile this. You're supposed to have R0, R1, R2, and so on. But for the sake of understanding, imagine register containing I, register containing J. So we compare these two things. If it is greater than this guy minus this. If it is less than this guy minus this. If it is not equal, loop. Okay, so very straightforward. If it is greater, this minus this. If it is less than this minus this. If it's not equal, loop. So you can see here, in terms of C code, also longer, right? But in terms of assembly, very compact. Thanks to this conditional code execution, you can really create some compact code. Okay. Then we have this confusing called if then. So for the UAL, universal language, right? Or universal. Okay, I think it's universal. Okay, for this we have this if then. What is it? If then? You can write something like this. You perform some comparison, then you write this if then else. Okay, so what is if then else? So if then else allows you to have 4 lines of code, where the first one is the equal. Okay, the equal block. The first line is for the equal, and the second line is for the else. Okay, so you can have ITEE or ITTE. T means then, E means else. Okay, so you can have 4 lines continuously marked as then or else. If the condition is fulfilled, you are going to run that. Else is not going to run that one. Okay, so I put a note here. You can have a quick one on this one. Okay, so oops, did I clear the thing? No. Okay. So let me paste this thing here. Okay, so this is what we call the if-then instruction. Okay, so it specifies that the if-then instruction makes up to 4 following instruction, which is called the it block conditional. The condition can be all the same, or some of them can be logical inverse of the others. Okay, so where is it? It's called the T means conditional. Condition following the condition set here. Okay, or could be else means inverse of the condition. So you can see here is IT X Y Z. So it could be IT T T E, or it could be IT E E E. E means else. Okay, so the 4 continuous code can be executed in the phone. So in this case, ITT equal. So this is the first one equal. The next one is T, that is also equal. True. Okay, so what about this one? ITTE not equal. So the first one is not equal. The second one, if it is true, then it's going to execute this one. The third one is equal, then it's going to execute this one. Okay, so you can have a look at this one, the paste one inside your chat. Okay, and have a look at that one. Okay. So I need a bit understanding to do that. Okay, so this is an example of that ITE. So in this case, ITE. Okay, so the equal, the first one is equal by default, and the next one is E else. That's the next equal. If you want to have the not equal, you can put it this one. So when the condition is not equal, it will execute this one. Okay. Now it's 3 p.m. So I'm going to give you 5 minutes break only. Okay, 5 minutes break only, and then we're going to come back and we're going to talk about subroutines. Okay, 1 minute to go. Okay, it's 3:05, so let me begin. So let's have a look at subroutines. So you can hear me, right? Let's check. Microphone on. Okay. Anyone can confirm? Yes, can you hear me? Okay. So what's a subroutine, also called function or procedure or method? So basically, it's just a part of your program where you have a single entry and single. Okay, and when you call the subroutine, what we need is this link register, like I mentioned to you before. The reason is because we need to go back to where we come from, okay? And the link register is responsible to keep that return address, okay? Otherwise, you call a function, you do not know where to go back to, okay? So the flow is as follows. So you have this main program running here, and then you want to call this subroutine or function or method or anything, something like that. What else we call it? Function or procedure, okay? Same thing, procedure, method, functions, they are the same thing. Okay, so we're going to go to this part by using what we call branch and link, and the return address, which will be the next line here. Okay, the next line here is actually kept inside the linked register. Okay, so when you call the function, you call branch and link. It's different than simply branch. If you just use branch, you cannot go back. So if you want to go back, you have to use branch and link, and the CPU is automatically going to save the return address, which is the program counter, into the link register. Okay, and when you want to return here, you simply call branch and exchange. Okay, so these are the two instructions we have: branch and link. Branch to an address and stores the return address, and we have branch and exchange. Branch to an address specify register and change the processor state depending on bit 0. Okay, so in our case, we don't have that ARM state and also the thumb state. So we are always in thumb state. So bit 0 will always be 1. Okay. That means we are always in thumb state. Okay. Okay, so this is an example of calling this what we call subroutine, okay, or function. So we have this main program, and we want to call that function, which is, let's say, called foo. Foo is a label. Actually, it's an address, right? But because we don't remember the address, we simply label it in memory. So we have this memory. So let's say the foo function is somewhere down here, foo, and this is, let's say, our main. Okay, and from somewhere in between at this particular line, okay, we want to jump to this function, and when we finish, we want to return to the next line. Okay, so this is where you use the branch and link, and we give the destination address. So in our case, we just give the label and let the assembler or the compiler resolve that label to that address. Okay, so we're not going to write the address ourselves. We're just going to give a name. Just like when you give a call to someone, you just select the name from the address book and let the address book do the translation from the name to the actual phone number. You don't actually remember phone numbers nowadays, right? Okay, so branch and link to foo. So this one go here. And then you have a couple of things like pushing and popping here. We're going to talk about this later. But the point here is that at the end of the subroutine, we're going to have a branch and exchange. We put link register here. This is where our saved address is. And this link register will be copied back into the program counter, and the program will then continue here. So why is it going to be copied back into the program counter? Because remember, the program counter is telling you the next instruction to be fetched. Changing the program counter means changing the direction of your program. Okay, so a big note here, you can read here why it needs to be set to 1. I put a note here as well. I cannot click the note. Anyway, just a note to this help why it is set to 1, but yeah, I think I need to open it in Acrobat perhaps. Exit full screen. How can I view the notes? Okay, never mind. Technical difficulty. Because actually I marked where is it written, so otherwise very difficult to find. Okay, let me try to open that using Acrobat. That is slide number 36. Let's jump to slide number 36. Okay, so yeah, this is the note. So RM is our register that indicates an address to the branch. Bit 0 of the value of RM must be 1, but the address to the branch 2 is created by changing bit 0 to 0. So it must be 1, but when you want to branch, it is actually automatically changed to 0. This is actually mentioned in page 142 of the STM32 Cortex M4 manual. So here, yeah. So this is where I marked for you. So this is a branch or branch link instruction. It says that for branch and link, or branch on exchange and so on. So you have this RM, right? The register, right? Yeah, that indicates an address to the branch where you want to go, but bit 0 must be set to 1. Okay, but the address where you are going is actually bit 0 equals to 0. So that is just how it is actually mentioned. Okay, so coming back to this one. Okay, so you need to have branch and link, and you need to have branch and exchange to come back. Okay, and the thing here is that in our CPU, okay, we have a set of registers, right? Which is R0, R1, R2, and so on. And these set of registers are actually shared by everybody that's running on the CPU. Okay, so this is our CPU. Okay, so if I have a main program, let's say we only have one program. Okay, this is just one program running on the system, and we have that main function, right? And from this main function, we jump to a subroutine, okay, called foo. Okay, so whether you are here or whether you are here, you are actually sharing the same set of registers. Okay. So the problem here is that what could happen here is that I might have some important information in these registers. Okay, some important values in this register, and then I go jump into foo, and then foo modifies those registers. And then when I return back from foo back to the main, the values of these registers has been changed by foo, okay, making it a corrupted state for main. Okay, so that's going to be a problem because we are sharing the same set of registers. So when I jump to you, you go modify the same set of registers, and when you return back, and I'm going to continue from where I left just now, but the registers have already been changed. So my result will be, ambiguous, or will be undetermined. Okay, after that, because somebody has changed my registers. Okay. So in order to avoid that, we have certain convention. Okay, the convention says that, okay, if you want to call a function, these are the registers you can change, and these are the registers that you cannot change. Okay, and if you want to change the registers which I said cannot be changed, you must first save a copy of them, then make your changes that you want, and before you return, restore back that copy. Okay, so that is the idea. Okay, so that is where the stack comes in. Okay, so Professor Munim has mentioned about stack in the morning. So stack is just a portion of your memory. Okay, a portion of your memory where you can store temporary data. Okay, it's normally used for storing temporary data, stack. Okay, and then we have some limited space on the stack. Okay, you can't have huge amount of stack here. It's kind of limited. Okay, if you want more memory, then you have another place, we call it the heap. Heap is where you declare dynamic memory allocation, and this is normally requested from the operating system. Okay, while stack is automatically created when every time you enter a function or go out from a function. So anything on the stack is normally called auto, right? Auto variables, which means they're automatically allocated and automatically deallocated, unlike heap where you have to control the allocation and deallocation. Coming back to this one, so in order for me to change certain registers, let's say I want to change register number 4, which is not allowed for you to change. may contain something important for main. I want to change it here. So before I change R4, I need to keep a copy of the current R4, and that copy is actually pushed to the stack. Okay, and once I make a copy of it on the stack, which means I push it to the stack, which means I write it to the stack, the next thing is I can do anything I like with R4. And once I finish my function, before I return, I will pop back the original R4 and then go back to main. So by the time you arrive back at main, the R4 is, nothing has happened to R4. It was the way it was left before. So the state is same. It does not change. Okay. So the operations to do these stack operations are called stack operations. Okay. So we have a couple of different instructions to do that. Generally, we just call it push and pop. But push means store. It's a storing memory operation, store. M means multiple. D means decrement. B means before. So store, multiple, decrement, before. While LDMIA means a load. It's a load operation because you're popping, taking it back from the memory. M means multiple. I means increment. A means after. So where am I storing or where am I loading from is actually the stack pointer. So stack pointer is our register. It's actually showing to the top of our stack, the memory location where we're going to read and write. And the exclamation mark here means that every time you write something, you're going to update the pointer. Every time you write something, you update the pointer. So you keep on adjusting the pointer as you push things to the stack. If you write 4 registers, you're going to adjust it by 4. If you're going to read 2 registers, you're going to adjust it by 2. So the stack pointer always moves around. Okay, and one of the things that you want to write to the stack is the list of registers, register 0, register 1, register 2, and so on. Okay, so this is a stack, a memory location. We have a pointer to the top of the stack. Okay, and the first one is showing here is push. I'm pushing a register R0. So we're going to write the data of R0 here and increment the stack pointer. And then we're going to push here. And then we're going to increment the stack pointer, and then we're going to push here, we're going to increment the stack pointer. That is not entirely correct if you follow this this convention here. Here it says push means store, decrement. Okay, decrement. So in this case, these addresses are going low here, as mentioned here, low. So every time I push something, the addresses is decremented. Every time I push something, it's decremented, and so on. And every time I pop something, I increment the address. Every time I pop something, I increment and increment and increment. In other words, if I push 3 times, it will go down 3. If I pop 3 times, it will go back to the original stack address. Okay, stack pointer. Now, that's where I mentioned just now increment and decrement, right? So we have different styles actually. Okay, we have different styles. We can have a stack which is ascending, or we can have a stack which is descending. But the style that we have in Cortex M4 is this one, that is a descending stack. That is, the stack grows towards low memory. Every time you push something, the addresses decreases. Okay, every time you pop something, the address increases. But you can also have a stack that is this way. Whenever you push something, the address increases. Whenever you push, you pop something, the addresses decreases. So we have 2 different styles of stack. Okay, and the only key idea here is that the stack has certain range only in memory. Okay, allocated range. Do not go above this range or go below this range. In other words, do not go outside the range. On Windows, you will have this error stack overflow. On the website, if you ask any programming question, it will go to the website stackoverflow.com. That's like the best place to ask question regarding programming, whether it's MATLAB or C or Python. That's a very famous website, right? Stackoverflow.com. It comes from this concept, this thing, Stack Overflow, where you put things on the stack until it just crashes over into the other region. Okay, so what happens if you go above this or go below the range of your stack? You're going to corrupt other things. So there could be other programs running here. There could be other things here. So other data here. So if you go above your stack, you're going to overwrite other memory location. If you have an OS, and it's going to stop you here and terminate your program. If you don't have an OS, then good luck. You are going to overwrite everything. Okay, but on certain compilers, the compiler is going to be very intelligent. If you allocate a certain amount of stack or array, for example, it's going to have an extra few more kilobytes of empty space as a buffer, just in case you just go across it. Okay, so depends on your compiler setting. Okay, so the key idea here is don't always play in the region, always be balanced. If you push 10 times, make sure you pop 10 times. Okay, otherwise the stack will be unbalanced. Okay. Remember I mentioned that there are two styles, incrementing and decrementing. So you can use any of the style you like. Okay. So we have these special instructions. We can have increment after, increment before, decrement after, decrement before. Okay. So what it means here is very simple. Okay, so let's say these are all our memory addresses. Okay, and our stack pointer is here, and let's say this is high memory, this is low memory, and let's say this address is 2004, and this one will be 2000, smaller memory. This one will be larger, 2008. Okay, let's say our stack pointer is at this location. So increment after means that if I push something, push the register R0. If I push R0, I am going to write R0 here and then increment my stack pointer to 2008. That is increment after. Increment before means I am going to increment stack pointer first. So stack pointer becomes 2008 first. Then I'm going to write R0 here. So that's the difference, increment after and increment before. Increment after means that the current location being shown is empty. Increment before means the current location being shown is already full, so increment first before writing. The same goes with decrement. Decrement is simply going the opposite direction. Okay. Okay, the following style, the following code shows you that R13 is my stack pointer in the ARM chip. Okay, R13 is stack pointer. The exclamation means update it. These are the registers that I want to push: R8-R18. This is R8, R9, R10, R11, R12. So shorthand is R8-R12. Perfectly fine, can be compiled, comma R14. So you're going to push R8, 9, 10, 11, 12, and 14. All of those things will be pushed onto the stack. And stdma means store. Sorry, load. This is load. Sorry, my mistake. That's load. This is store. Store means writing to the stack. The only thing here is that there's no exclamation mark, so it's not doesn't get updated. Okay. Yeah. Okay, so a quick one. Push R4 to R7. So this is increasing address. Okay, let me just check what is push. Push is, where is push? It's written somewhere around here, right? Anyone can show me what is push? Yeah, so push is store multiple, decrement before. Okay, store multiple, decrement before. Okay, so this is our address of original stack pointer, and I'm going to push store multiple, decrement before. Sorry, I also don't remember. So R4 to R7, R4, R5, R6, R7. So this is 4 bytes, 4 bytes, 4 bytes, 4 bytes. That will be 4, 8, 16 bytes. Is that correct? 16 bytes of memory. Okay. So decrement before. So my current stack pointer is here, original. Decrement before, decrement by 16 bytes. So 1, 4, 4, 4, 4. Decrement by 16 bytes. Then you write R4, R5, R6, R7. So you write R4, R5, R7. Okay, so that's how you write it. Okay. Okay, so of course, my explanation a bit wrong. Okay, decrement before means you write decrement, you write, you decrement, you write, you decrement, you write, you decrement. So in this case, you will write 16, where the top of the stack will be R4. Okay, your top of the stack will be R4, and then you're going to have R4, R5, R6, R7. So that's actually how you do it. So decrement before means you decrement the address first, then you write it, decrement the address, you write it, decrement the address, you write it. That will be 4 times. Okay. And the order will be R4 will be on the top of the stack. What about popping? It's just the reverse. In this case, pop. Actually, pop, I can write this. Let me just cancel this and pop R1 to R4. R1, R1, R2, R3, R4. Correct, 4 things. It's not necessarily pop. It is not necessarily pop R4, R7. You must understand this. So you have the CPU, R0, R1. Let me just, oops. Okay, this is my CPU. Okay, I have R0, R1, R2, R3, R4, R5, R6, R7. this example, I'm pushing R4 to R7. So R4 to R7 is pushed onto the stack. Later, when I want to pop, I can always pop like this, R1 to R4, let's say not R1, R0, R0 to R3. I can always take this thing and pop into these registers. No problem. So don't think that if you push something from R4, it must always be popped into R4. No, you can push from R4 into the stack. Later, when you pop into R6. Not an issue. And what's the point? What's the important thing here is that if you push 16 bytes to the stack, when your subroutine finishes, make sure you already completed unrolling the stack by popping 16 bytes of data from the stack. Okay. Okay, so this is the same thing. Load.
But if you pop back to a different register, right now, let's say if you context switch back into the main program, then wouldn't the main program variables be looking for it in the old register name, like R4? But you put the
Correct. Okay, so yes, that's true. So for the purpose of saving a context, okay, so for the purpose of saving a context, if you're saving those registers, let's say R4 to R7, when you pop them back, you pop them back into R4 to R7. You are right. For the sake of context, it must be the same, okay, because you're doing context switch, right? But generally, I'm just talking general, nothing to do with calling a subroutine or what. If you push something into the stack from R4, when you're in the pop, you can pop into R1. It's not a problem.
there's no issue lah. Okay.
No issue. You don't always think that if I pop in this order must push also like that. No, it can go into any registers you like. But in the case of what you say is true. That if the purpose is to save those registers, then when you pop, you must pop in the right registers. That's correct. Okay. Okay. So again, this is the same example. Increment after R3 and R7 only, and this is R3 to R7, so 3, 4, 5, 6, 7. So there's a difference here, comma and dash. Okay, so this is the idea. So when you call a branch and link, it's going to call that subroutine, and you need to, in this case, if you only have one subroutine, it's okay. Okay, because branch and link, this program counter, the moment you call branch and link, this program counter is automatically saved into link register. Okay, the problem here is that if I call a subroutine here, and this subroutine is calling another subroutine, so this branch and link, okay, so remember, let me draw a link register here, link register, okay, create this one. So when I call the first branch and link, this one, when I call the first branch and link, when this foo finishes, it needs to return here. Okay, so it needs to return here. So the return address here, PC1 plus 4, is automatically saved inside your link register because of branch and link. Automatically done. So not a problem. The problem is here. The moment you call another branch and link from here, this guy, the bar subroutine, needs to return to PC2 plus 4. So this branch and link will replace this with PC2 plus 4. So it goes into here. That's not a problem. The bar can come back to foo, but the foo cannot go back to main because its return address has already been overwritten just now. Okay, you get the idea, right? Because you only have one link register, so it can only save one register to go back, one address to go back. So if I go jump into a subroutine and that subroutine calls another subroutine and that subroutine calls another subroutine and so on and so on and so on, I can only go back one stage back because I only have one link register. So to overcome this issue is where you have this stack. Okay, this is where you have your stack. Okay, so what you do here is that the first time you call branch and link, and then this link register, because I'm going to call again, so this link register I push onto my stack, push. So the next time I call branch and link, this branch and link is going to replace my link register, but no problem because I have a copy on the stack. So the moment this guy finishes, it's going to pop its link register to return back here. And before I call my branch and exchange here, I'm going to pop my link register and then call branch and exchange, and I'm going to get back the correct address to return back to the main. Okay, so the key idea here is that you only have one link register, so you can go one stage down. Okay, If you have multiple subroutine being called inside and nested, call, you only can go one back. So you need to keep your link register yourself. You have to do this manually, okay? But manually means if you write in assembly, if you write it in C or high level, the compiler will handle this for you. Okay, so this is another example, quick one, branch and link to quad, and then quad needs to call SQ square. So before you go here, you push this guy, can go here, and then the moment it finishes, you want to call again. You don't have to push again because the same link register, right? Okay, then you can call again, and then you come here, you pop again. This link register is for quad. Okay, then you branch and link exchange, it returns back here. Okay. Okay, so if you call the subroutine and do the push 457 LR, when you want to return, you pop again 457 LR goes to PC. Makes sense, right? Because LR is saving the PC. Okay, LR is saving the PC, the next program counter or the next instruction to be fetched. So that's actually the PC. So when you push it, you're pushing the link register. When you're popping it, you're popping the link register straight away into program counter. This is effectively a branch and exchange. Okay.
Doctor. So,
Yes.
so for this push, right? So because of many register, which one will we push first?
The smaller one first, 457 and so on. Okay, even if you write it this way, R5, comma, R4, comma, R7. Can you write it this way, right? 547. But you will write in the memory 457. Okay. Okay, so next one. Quick example. Okay, 47 out of 92 with 30 minutes to go. Okay, actually at the end, a lot of the slides are just repetitive of what we have already covered. So should be okay. So in this example, okay, we have, this is the main function and this is the subroutine. So main and number equals to 0. So you get the address of the number and then you load the number into register and then you add that with 25. Oh, sorry, this hey, this is the main. You get the number into R1 and then number equals to 0. Okay. And then store 0 into number, branch and link to exchange. Branch and link to change. So change is our subroutine. So this is where it will need to keep the returning address. This is the returning address at B here. Okay. So this will jump here and then it will execute here and then it will call branch and exchange link register. So this will automatically return back here. Okay. The rest are just a processing. Okay, so this is again another example for nested subroutines. So we have this random 100. This guy is being called by somebody. So you have a main is calling random 100. Random 100 is calling divide. So nested. Okay, so somebody is coming from main here. So the first thing is saving its own link register. It's saving its own link register. Then it calls random. So it goes into. There's no random here. Oh, I guess it's another function called random. Okay. Okay, whatever, there's a function called random and you come back from random, you come back here. Then it calls divide. And then we have a sample of divide here. So you perform divide and then branch and exchange link register. It's okay, the link register is keeping the return address to random, not to main. Okay, so it comes back here. And then I pop this one. This is a pair. This is a pair, can see that? I push, I pop, I push, I pop. So I pop back this one and then I call branch and exchange to, and this will return back to main. Okay, there's a branch to random. It's not shown. It's not important. The important thing here is that it is a nested. Main calls random 100. Random 100 calls divide. So because you have two link registers here, you need to keep two of them. So the first one you push to your stack. When you finish, you pop from the stack before returning back. Okay. I think we talked about reset, subroutine, and stack. So when you start your CPU, one of the most important thing here is that the first thing you need to initialize is the stack pointer. Okay, so that's the first thing that you need to initialize upon power up, because we need a stack to do all of these things, to keep our temporary variables, to do jump into functions and so on. Okay, so and then by default the link register is garbage, is initialized at the reset to FFFFF. Okay, and thumb bit is set because in Cortex M4 there's no ARM state. There's only thumb, so forever thumb. Okay, and that's all. Okay, So the important point in this slide is this. Okay, so we need to initialize our stack pointer at the beginning of our program, of the boot up of our system. Okay. This is just a demonstration. So you have move, you have add. This is an add operation. And then when you have this return, you branch and exchange link register, returning to where? Returning to the caller, which could be the OS. This is the main function. It's being called by the OS and returning to the OS. So branch and link to the OS. Okay, so it goes back to the OS. Okay, what about this one? Local variables on the stack. So we have x1, y16, temporary x, and some operations here. And this is a subroutine called swap. Okay, so in this case, I'm trying to save 3 variables, 1, 2, 3, and these are all integers. So 4 bytes, 4 bytes, 4 bytes, that makes up 12 bytes of memory. Okay, so these variables are actually alive on the stack. So if you have your stack of your function, so in your stack, you have that x, y, and temporary. And these are why we call it auto variables. So the moment you exit this will be automatically deallocated, because once you exit your function, your stack also automatically get destroyed. So every function call has its own stack. Okay, so when you crash a program, you get a stack trace. Okay, a program crash at this line, coming from what function, coming from what function, coming from what function. So how do you know who calls who? So it's that you have this stack trace. Okay, so the moment you exit this function, these variables will be destroyed. That's why we call it auto allocated, automatically deallocated. Automatically means in terms of lines of code, you have to write the code to allocate and deallocate them. But auto means that when the compiler do it for you okay, if it's in C code, a compiler does it for you. So auto for you, don't have to do anything. But in reality, of course, it translates to code. You have to have the code. Okay. So we are making 12 bytes of space, 4 times 3, 12. So 12 bytes of space. We're going to take the value 1 into R3. So that is the X. And then we're going to store X at the top of my stack. Okay. And then I'm going to increment the stack by 4 and then put the value 16. Then I'm going to increment the stack by 8. And that's the value. Temporary, that's temporary. Okay, temporary. Okay, temporary. And then you're going to put Y into X. So you load from the stack. This is loading the variable from the stack and then storing it back to the stack. So you're working in the stack, reading, writing onto the stack. Okay. So working with stack is a bit slow. Okay. So if preferably you want to load everything inside your register and work within the registers, and once you're done, then only you write it back to the stack. Okay. So the further you are from the registers, the slower it gets. The fastest is to do everything in your register. Then the next stage is memory. The next stage is your hard drive and so on. Okay. So once it goes all the way down to the drive, then it becomes very slow. Okay. So how do you call a function? We need to do parameter passing. Okay. So we have some code probably in C. We have some code probably in assembly. We may have some pre-compiled libraries in C, such as math.h and printf. Probably they already recompiled, so it does not waste you time. Every time you want to compile a program, you have to recompile the standard libraries. That's a waste of time. Okay, so probably pre-compiled. Okay. So when you have separate files in your project, some files will go through an assembler, some files will go through a compiler, C compiler, while others are already pre-compiled. They only need to be linked to. So all of these things, the object files will go to a linker where you're going to generate the executable file. Okay. So in order for you to combine files that's coming from a C compiler, combine files coming from an assembler, you need to have a fixed convention. Okay, so in the ARM, it's called the APCS. That is the ARM procedure called standard. Okay, so it's a standard, which is why you can take your C code and compile using MKEL and get an object file. And then you can take an assembly file and compile using an assembler from a different company. And then you have another C file compiled using IAR compiler. As long as all of them follow the same procedure called standard, you can link them together. Okay, and you should get a workable, what we call a workable, executable final program. Okay, okay. So how do you pass parameters through your function? So let's write a simple function here. So we have main, that is our main function. And inside our main function, we have variable A and we have variable B. And notice these variables are integers. And then I'm going to call a function called add, which is going to take A and B and return the value in another variable called M. So let me add another M here. Excuse me for this kind of rough writing, maybe missing semicolons and stuff like that, but the idea is to show the core concept. So I have the function add here, or a subroutine, which takes the parameter A, comma, which takes the parameter B, and then returns an integer type. And the thing that it actually performs here is that A plus B into C, let's say integer C, and returns that C. Very simple like that. I hope you understand. We have A and B passed to function add as A and B. In function add, you perform A add B into C and return C, and this C is returned back to the main and captured inside M. Okay, so it's a very simple function here. So how can I pass A and B to the function add? How can I pass A and B to the function add? Okay, so we have three styles. One is pass using registers. Second one is pass using the stack. The third one is pass using registers and stack. Okay, so this is the way how we're going to pass A and B to the function add. Okay, so A and B are actually parameters to the function add. Okay, so how do we do that? So the first one is set the registers which contain the inputs, which means what are the registers that contain A and B. Call the subroutine by calling branch and link. Inside the subroutine, you expect the inputs are in register following A and B. You perform the operation on A and B, and you place the output in an agreed register. And when you return back, the main program is going to take it from that register which we have agreed. So you can see here we must have some agreement. You know what? If I want to pass you something, it will always be in this register. You know what? If I want to return something to you, it will always be in this register. So the convention is parameter 1 will go through R0, parameter 2 will go through R1, parameter 3 will go through R2, parameter 4 will go through R4, additional parameters will go through stack. Whatever values you return will always be returned in register R0. Okay, so that is the convention. That is why, in order to have an efficient and fast function, do not have parameters exceeding 4, because that will give an impact on the performance. Okay, can I pass it to the stack? Also can. Push all the inputs onto the stack. Call the subroutine using branch and link. The subroutine pops the inputs from the stack, performs the action, pushes back the output to the stack, calls the main, returns back to the main function. The main function pops the result. This is the result. Okay, the output from the stack and finish. Okay, so that is the style. Okay, so the style is APCS, which defines what are the registers to be used, the stack convention, and then the trace data structure, argument passing result, and blah blah blah. Okay, so you must fulfill this APCS, and you will live happily ever after. You can compile with other compilers that follow APCS. They are binary compatible. That's why we call it binary compatible, which means that if you try to link them together, should be no problem. Okay, so these are the things: R0 to R3 passing, R0 to return. Okay, functions can freely modify R0 to R3. Okay, so you don't have to push this. You can happily modify. So the calling function and the caller both know R0 to R3, anybody can modify. So if there's anything important before calling the function, you push it back. Okay, otherwise you can change it. But R4 to R11 is not it's not owned by the function. So if you want to modify R4 to R11, the function is responsible to keep, to store, to make a copy of these registers before modifying. Okay, if you, so this is the responsibility of the caller. This is the responsibility of the function itself. Okay, so the function, if you want to modify this, you have to save these registers because someone owns this. Okay. So this just in terms of a table, these are your arguments up to 4, anything, general purpose, intra procedure call, stack pointer, link register, program counter. Okay, so example, I want to call this function. I got two arguments, R0 and R1. So this is in R0 and R1. So this is my subroutine. Okay, so before calling this, make sure the values are in R0 and R1. So in this case, R0 is 3, R1 is 4. Then I call SSQ. Okay, goes to SSQ. It expects those things are in R0 and R1. So these are the inputs. And before I return the answer, I put back into R0. That's the convention. This must be in R0. Okay, so when I return back, R0 is the answer, and I can do whatever I want with R0. Okay, parameter passing register, another example. Okay, here's the main function. Huh? Call a subroutine that uses registers for parameter passing. So I have the 7 into R0, I have the 3 into R1, and then call exponential or x, whatever. So this guy calls this guy, and then it uses R0, it uses R1, blah, 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 blah. And before it returns, the result is YY, okay, and or which is 1, and it moves it into R2 and return. So is this compliant? Anyone?
No,
No. Why is it not compliant?
not R0.
Yeah?
Because result is not stored in the R0.
Correct. So this is not compliant. This must be R0. Okay. So I think you understand this already. Okay. Passing through stack. So we have several values here. Okay. And then we push everything to the stack. Okay. And then we call the function. This is a function. We pop everything from the stack. Not everything. Like in this case, in this example, it's finding the max value. So it's popping one by one. It's check the first one and then compare, and then it loops, and then pops the next one, and then it loops, it pops. But it will pop 4 times because you push what we call 5 things. So it's going to pop. The first one you pop already. So you need to pop another 4 more. So 4 more to go. Total 5 times. So if I push 5 things, then make sure you pop 5 things. And in this case, this function is finding a max. It's not popping all the 5 things in one go. It's popping one by one and doing the comparison. Once it gets the answer, it moves the answer to the max. New number is the max. And then branch and link exchange. So max is Rn2. Okay, doesn't matter because the answer is not returned from the register R0. The answer is actually pushed to the stack. So from here to here, I push 5 times. From here to here, I pop 5 times. Before I return the function, I push the answer 1 time onto the stack. Then I return here. Then I pop the answer 1 time from the stack. Okay, so the stack is balanced. That's the key point here. Whatever the function is doing, is just finding a max. You go through the line, you understand how you find the max. The key point is picking up one by one. I push 5 times, you pop 5 times. I push 1 time, then you pop 1 time here. Stack and register. So some things are going through registers. Going through stack. Okay, stack. So here, this one is finding the min max. Okay, so it's now pushing R1 to R3 onto the stack also, and then it's popping the top of the stack into R2. So remember, this R2 and this R2 is no longer the same. This is a temporary R2 he's using because he already pushed R1 to R3 onto the stack, and so on. Okay, so I'm not going to walk through you this. Okay, but the key point here is that these are being sent through registers. These are sent through stack, and then you go and further push onto the stack because you want to make a copy onto the stack before using those registers to do some processing, and then popping one by one. Then before you return, it returns the result in R0. Okay. Okay. What about nested subroutines? So we have covered this already, so we can go very fast. It means that one function calls another function, another function calls another function, another function calls another function, and so on. So the key point here is that you only have one link register. So if you're going to call many times, it's your responsibility to keep the link register onto the stack. Otherwise, you cannot return back. So from here to here, the return address in link register. From here to here, the return address is in this link register. This is overwritten. So you need to push this to the stack. From here to here, it's written using link register. If you don't keep this link register, then this is overwritten. So you need to push this to the stack. Okay, so I think you get the idea. Okay, function entry and exit. This is just demonstrating to you that before you enter a function, you save those registers and the link register. Before you exit the function, you restore the registers and you pop the link register into the program counter to return back from where you are. Okay, so what are the registers you want to save and not? You can save all the registers if you want. Okay, but there's going to be a waste of time, right? So if you're writing your own function, you will know what are the parameters going into the function, what are the registers you're using, so you can decide whether you want to push the registers or not, which from the main function. I'm not going to use this register, so no need to push. Okay, I'm not going to override it, so no need to push. Okay, if you write in high level language, the compiler is going to decide that. The compiler is going to see what registers are being modified and not modified, and going to make a best guess on it, and based on that, it's going to push or not push depending on the compiler. Okay, so this is where I talk about heap. Heap is where you ask memory from the system dynamically. So in C programming, you probably have come across memallocate, memory allocate, which is a pair with free. Okay, in C++, it's called the new pair with delete. So it's your responsibility to allocate and deallocate. So this is what we call dynamic memory. Okay, dynamic memory allocated from the system, but it's your responsibility to allocate and deallocate. But things on the stack is called auto. If you write the code in high level, it's automatic. It's been declared on the stack and automatically unrolled from the stack. If you write in assembly, then you have to do everything yourself. So far, if you see all those examples in assembly, you have to do everything yourself. Okay, you make the wrong push and pop, the stack will be unbalanced. You run the program for 1 hour, okay, 2 hours, okay. After 1 day, everything crash. Okay, because it's like a slow leak, 1 kilobyte, 4 bytes, 4 bytes, 4 bytes. You never know, 4 bytes per second, or maybe 4 bytes per millisecond. Okay, works fine for 1 day. After 7 days, it just crashes. Okay, that's stack overflow. Okay, and so it's your responsibility to make sure it is correct. Okay, so this is also called memory leak. By the way, memory leak has something to do with dynamic memory, nothing to do with stack. Okay, memory leak, where your program allocates some memory, never releases it, and you open Chrome, you open one tab, memory goes up by 100 megabyte. You open another tab, it goes up by 200 megabyte. You open 1,000 tabs, 100 tabs, it uses 8 gigabytes of memory. You close all the tabs, leave one tab, still 4 gigabytes of memory. Something is leaking somewhere. Okay, so that is very hard to find also. Okay, so what is this? I think this is nothing special here. Okay, a procedure often accesses operands in the following ways: an argument passed on the register, so no further work; an argument passed on the stack, so you need to use a stack pointer with an immediate offset known as the compiling time; a constant, PC relative addressing; a local variable allocate on the stack; a global variable allocated in the static area and can be accessed by the static base relative addressing. So I'm just telling you where things reside in memory. Okay, same thing, procedure, storing data from the stack, storing and popping. Okay, function calls. So this one calls this one, need to push link register. This one calls this one, push listener pop, and then pop. Okay, and of course you have the parameters. This is one parameter R0. Okay, this is another parameter R0, and so on. Okay, so nesting recursion requires coding convention. So we have the coding convention, so nothing to be worried here. In this case, it says that, okay, pass value 5 to function 1. So the 5 is moved into R1, and then you store to the stack, and then you call the function. So in this case, the function is accessing the variable from the stack. Okay, but we already have the calling convention already, right? What registers to use and how to use the stack. What about this one? Here's a main function. Okay, that's continued on the next slide. So this guy is calling the function 1, right? And the R1 is on the stack, right? So here you are loading from the stack, okay? Loading argument from the stack. Okay, and then here you want to call function 2. This is actually coming from this example. Okay, calling function 2. So again, you need to keep your linked register. Okay, store function 1's return address. Okay, so you need to keep this because and this is manually done. Okay, so you push this onto the stack. Okay, and then you also push the argument that you want to pass. So you're also using an argument passing using stack. So you don't push the argument first, then you push the address, and then the order will be out of order lah. So you push the return address first, then you push the argument, and then you call the function. So on the top of your stack is actually the argument. Okay, that's the last thing you push on the stack. So on the top of your stack is actually your argument. So when you come into this function, this call to function 2. Where's function 2? Here you are, function 2. You pop this guy, immediately you get the argument. Okay, immediately you get the argument. So, so these 3 slides is coming from the simple C program here, demonstrating to you a couple of things: the need for the link register, the need to, in this example, using the stack to pass the parameters, the need to push and pop, and the same arguments, R0 here, R0 here. Okay, and the moment you return, you need to pop the link register. Okay, so that you can return back from where you are. And in this example, there's nothing been returned. Okay, the functions are all void, so nothing has been returned to the caller functions. Okay, finally, I like the word finally. Okay. Okay, so this is inline assembly. What is inline assembly? Inline assembly means that you have a C code. This is a C file. It is a C file. Inside a C file, you can have a block of code marked by certain tag. In this case, the tag is _ASM. And then you open a curly bracket. And what you can do here is you can write a completely valid assembly code. Okay, so inside your C code, you can have assembly code. Okay, so this is what we call inline assembly code. So assembly code inside your C code. So the tag here, you just have to double check. So I guess this is correct, _ASM for ARM, but for different compilers, the tag is different. Okay, so I think for Microsoft compiler, the tag is different. Okay, sorry, because I use a lot of Visual Studio, so the tag is different. So whatever the tag is just to mark the region where it is assembly. And when the compiler runs through it, it will consider this assembly code and compile using the assembler. Okay, and when you have this assembly code here, you can use, this is actually R0. You can use this as R0 perfectly fine. Or you can just use the names here, and it should compile perfectly fine. Or if you don't want to use the name, this is actually R0, this is actually R1. Okay, you can use that. But if you use the name, it should compile perfectly fine. Okay, but this is where you do this when you want to have speed. Perhaps some of the things you want to control manually in assembly. So this is how you do it. Okay, you think you don't have enough control in high-level language like C. You want to go to assembly. So certain portion of your code can be written in this assembly block. Okay, but this does make your life difficult. What happens is now there's my _string copy, which is a C code. Now this is actually tied to ARM. Okay, so if tomorrow I want to recompile Photoshop, okay, and this is, for example, this is an ARM Photoshop, and I want to compile for x86, I can't just take my C code and recompile it because portions of my assembly code, portions of my C code actually contains ARM specific assembly code. So now you have to tell the engineer to, you know what, I need you to convert this assembly code here to x86 compatible. But if it's everything in C, easy lah, you just recompile with minor modification. Okay. But in typical applications, 90%, I can say, will be C, maybe 10% where high performance code or very specific hardware code will be written in assembly, which is why if you have Photoshop for x86 today, tomorrow Apple comes up with this M1, right? It's an ARM processor. It only takes a very short time for Adobe to recompile the Photoshop for ARM. Okay, because not much changes. Probably 90% of the program is already in C. Some miscellaneous issues. What is a startup code? You need the startup code. This is like a boot up code. When you turn on your laptop, right, or your computer, you have this firmware, right, that needs to initialize the hardware, right? So you have the same thing in your system before it actually runs your OS or before it actually runs your single program. Okay, you need to boot up the system. This is where you have that startup code. Okay. So some of the things the startup code does is that it disable all the interrupts because imagine you wake up this device and you're already capturing the keyboard input and touchscreen input and stuff like that. So the routines for handling these interrupts are not even ready yet, and you're already accepting interrupts. So that will be very crazy. So during boot up process, all these things are actually stopped. Okay, and then some things are being loaded from ROM into RAM. Stack pointers are initialized, data memories are initialized, okay, and then heap is now being created that is for dynamic memory, and then before you begin your main function, you enable the interrupts. In other words, it's initializing the system. So if you boot up your handphone, Apple phone, you'll see the Apple logo and the spinning thing, right? If you boot up your Android, you'll see that Samsung logo for like a good 30 seconds. That's actually booting up. That's your startup code. Even after that logo, maybe you cannot proceed to the Android OS. It just hangs there. That's a different issue, lah. So, but you have the startup to initialize the hardware. Okay. So typically, the startup code will also include a few instructions after the call to main. This instruction will be executed only in the event that the high-level language program exceeds. You might want to use this instruction to halt the processor, reset the system, or transfer the control to the debugging tool. So when your program ends, also maybe you have some extra things to do. That's under the what we call the startup code, lah. Okay. When you shut down your computer, Windows shutdown, it sends a signal to the firmware. The firmware then actually shuts down all the devices on the platform. Okay. Okay, so in case the programmer doesn't want to have the default startup code, he must assemble himself. Include the resulting object file among the list of input files to the linker. So by default, if you build a project in MKEL or GCC, you get some default startup code. If you don't want, you have to do it yourself and make sure you link it with your main project. Okay. Okay, so it's already 4 p.m. So I think I'm going to finish in another few minutes. Okay, so a very minimal startup code. Okay, text means code. Global means this is a function that is exported out, can be called from outside, and the name is startup. This is the label, and then a very simple thing here: move 0 to R0, move 0 to R1. There's a label to back into the link register and branch to your main function. Very simple startup code. Okay, and if you're using a GCC compiler, you have some commands lah: compile, output. This is the object file for startup. Okay, the output name is startup.o, and the file input is startup.s, and stuff like that. Okay. But of course, we build with MKEL. You will probably look something like this in your project. There's a .s startup file. You can double click and open and see inside. Kind of long code also. Or you can use a configuration wizard. You can just check what are the things you want, and it's going to generate the startup file for you. Okay, and finally, this part is just talking about device driver. So what's a device driver? Device driver is a way for you to communicate to the hardware, okay, through a software layer, in this case, a software layer, okay, and hide what are the details. So, you have this printer, and you have the printer device driver for the printer, HP LaserJet or Canon printer whatsoever, right? So the operating system or your software talks to the printer through the driver. Okay, so the driver is like the translator to the actual hardware commands to the printer. So I don't really need to know how does a printer works, or Microsoft Word really doesn't need to know how the printer works. It just needs to say that, you know what, print Times New Roman at coordinate 00 with black ink, color R0, green 0, blue 0, done, that's all. Okay, so it sends a command like that, and the actual printer driver translate it to the actual commands to the printer. So that's a purpose of device driver. Okay, so you don't really need to know the details. All you need to know is the public interfaces. So the private interfaces are hidden. You don't really need to know. So in this slide, it's written there public routines and private routines. Okay. So this example just showing you a couple of drivers for LED. We have LED initialize, we have LED off, we have LED on, we have LED toggle. So in our main program, we just call LED init. Then when we want to turn off the LED, LED off. When you want to turn on the LED, LED on. When you want to toggle the LED, LED toggle. We just call those functions. So the details may be like this. Okay, so a lot of details inside, setting the clock, getting the address, setting some bits on the clock of a pod, and then do something blah, blah, blah. So initialization may be many lines, but this is actually hidden in the device driver. You just call LED init. Okay, so from your main program, you just call LED init. So again, for off and on and so on. So the key point here is that the driver is a way of abstraction. Okay, so the details are inside that driver implementation. So if you have some commonly used drivers, commonly used interfaces, they probably come with their drivers of their own. So if you want to interface to an LCD 128 by 64 pixel LCD, a small LCD coming from company A, most likely it comes with the driver. You just include the library inside your project and you use the public interfaces to control that display rather than knowing every bit and every register inside that display. That's no longer necessary. Okay, so that's good as an abstraction. And the other good thing is that if there's a fault with the way of how it works, you can always update the driver without changing your program. Okay, so you don't have to change your program. The interfaces remain. The driver details may change. Okay, so efficiency. Bit talking about efficiency. Efficiency means minimum input, maximum output. Okay, that's what is efficient. Okay, use the least amount of effort to gain the maximum output. Okay, that's efficient. So if I can stretch $1 to survive a week, that's very efficient, right? So why we to be efficient? Because it gives you competitive advantage. So your software can run faster in less space. I think one good example is probably iPhone and iPad. Okay, they come with less RAM, I think, and probably slower processor, but they run so much smoother than Android and so on. Okay, you may argue, I cannot say for sure, but it does feel that way. I guess maybe it's more efficient. Okay, using the hardware more efficiently. Then if you have an efficient software, which means you can do work faster. When you can do work faster, you have more time spared. So when you have more time spared, you can add more value-added functionality. Okay. So you can add animation, you can add more complex algorithms, you can make it better because you have so much headroom, you have so much time to do other things because you're already efficient to begin with. Okay, so those are some of the reasons. So other than that, it's cheaper to build a device because you can use cheaper and smaller microcontrollers, which makes it more applicable for more markets, okay, because of a lower price point. So how can you make something efficient? One is optimization. This can be done by the compiler. Okay, so the compiler can identify sections of a code that can be made optimized, how aggressive or not. Okay, you can use better algorithms. So an example is sorting. You have bubble sort, quick sort, insertion sort, selection sort. So there are different ways of doing the same thing. Okay, but some of them are more efficient than the others. They use less space in memory, or they can get to the end result faster in less number of steps. Okay, and the final one is use assembler at the right place. What it means is that the desire is, of course, to do everything in high level because it's easier, but where it is necessary, it's good to use assembler. Okay, some things are slow on ARM, such as floating points, so most low-end ARMs do not have that. Division is also slow because there's no native instructions for division. It's normally done in software. And reading unaligned memory accesses is a big penalty. So Associate Munim talked about this in the morning, I think, when he was talking about the memory, right? Or was it yesterday? Okay, so at the end of this slide, you can just look at some of the code examples. And among them are this one. What is this?
Can skip lah.
This one can skip. I'm not going to explain. I'm just having a look. This is summing some values. This is bubble sort.
Yeah, just
This
collect
is
some just
cipher.
random things from internet.
Yeah, this is cipher, and that's all. So that's all. So at the end of this one, you just have a look lah, for fun. I think you should look at bubble sort lah. I think bubble sort is easy to understand lah. Okay, I mean the theory is simple. This one I do not know the theory, so I will look at it. So just some examples. You can have a look at the back. These examples. You can ask some questions now, or the class has ended. But these examples, they really demonstrate some of the concepts and some of the instructions that we have studied. If you look here, even complex examples like this hyphens, so you don't really need to know all the instructions in the ARM instruction set. If you know AND, load, move, exclusive OR, what else? Subtract, test, load, register, compare. Basically, if you know those important instructions, 90%, 80% of most problems can already be solved already.
Prof, maybe can give like a list of commonly used assembly instructions so that so that it'll be easier for us.
I think the one that we covered in the class are all those what we call normally used.
Yeah, already given, I think.
Yeah, those are the only not normally used. So
because for ARM, there's not many. It's unlike x86.
yeah, so I think that is one of the advantage of ARM as well. So the instruction set is it's not that many instructions. Reduce instruction set, reduce instruction set. So they're not many. So if you look at the slides, whatever you see in the slide, if you can understand all these instructions, that's it, enough. And that one cover 90%. 80% of any application out there you can solve with this. And I think 99% of all the questions that I'm going to ask, PM is going to ask already nothing more than the instructions we have here. I do not know, maybe PM Munim this time wants to ask really obscure instruction.
Like C set GES something.
For me, no lah. I can only
just move, load also good enough. Move, load, and then a few arithmetic instructions, enough lah.
Yeah.
I hear a lot of people last semester fail this subject. So
you want exactly which instruction? That's too bad.
Yeah.
You'll never get it.
Actually, we have a list of instructions. Normally, we give that. Later, I put it online. I'll give to PM Munim as well. It's just one piece of paper, the normal instructions we use.
Okay.
Yeah.
Prof, can you go to the slide number 42 about the push command?
Okay.
Push, 41 maybe 41. So I just understand that. So the STMDB, right? So it means that after decrement, then only it before. Sorry.
Okay. So
before transfer.
So there are two styles. One style is this. Okay. Imagine my stack pointer is showing to this location. Okay. Okay. Let me put this one. Okay. This address 1004. This is address 1008. This is 1008 plus 4 is what? A. Okay. In hexadecimal A lah. Sorry lah, my hexadecimal not so good. Okay. So imagine this one. So this is decrementing. This is incrementing address. Okay. So imagine my stack pointer is pointing to this location in memory that is address 1008. So the first question is that when the stack pointer is pointing to this location, was it a location or is it a location where there is already a data here? That is the first question. Is the data already here or the location that I'm pointing is currently empty? So that is the style of your stack, which is set in your program to use the same way. So if your stack pointer style, the way your system has been programmed, is that the stack pointer always points to an empty location, which means this data here is incrementing. It always points to an empty location. So if it's always points to an empty location, you want to write the data first, then increment. Write the data first, then increment. So if you're pointing to an empty location, so increment after. You write first, increment after. Write first, increment after. You don't increment first. If you increment first, then you're going to leave an empty location. You're going to waste memory. Okay? Okay, but if your stack pointer is already showing to a location which is already full, the last full location. Okay, the last full location. Your stack pointer ends at the last full location. So in this case, you must increment before. So you increment first, then write. Increment first, then write. Increment first, write. And when you stop, you always show to the full location. So this is what we call empty stack and full stack. Okay, so that's a term there. Is there a term there in this slide? Or maybe we have removed it for avoiding confusion. Empty ascending.
No, it's full descending and
Yeah. So yeah. So in this case, if it's pointing to the full one, is full lah.
and then this step in the slide is actually reversed. Increasing address going up.
Oh, okay. No. Because I put here, this one is 1004 small address, 1008 a big address. So yeah, I'm just showing decreasing is there, increasing there. Yeah.
The
So
source of
for-
confusion.
One question. So in the slide here, example is the decrement before, right? You say that.
Yeah.
So it should be decrement, then it's store. Then
Yeah.
is it store start from R4 or R7?
I start from R7. That's the way it always look like this. Yeah, I mean, this one increasing here. I wrote it increasing this way. So, what this is what Intel style or what? So it doesn't matter lah. The important is what I mark here lah. So if increasing here lah. So if you want to make it correct, then this will be A, this will be 4, and this one whatever lah. So this one is increasing this way. So large address here, small address here. My one is large address here, small here, just to make you confused, and also make me confused.
So usually when you start to push, it was push from the behind first. I mean R7 first until the R4.
Actually, what it means is that the top of the stack will be this one. So stack will be this one. So you can say it that way lah. If you push R7 first, R6, R5, R4, you can say it that way lah. But the top of the stack will be the small register lah. It's just it has always been that way.
Okay, understand. Okay, thank you.
I think the default is this one.
Yeah, the default is this one. So if you want to avoid confusion, just use push and pop lah. Okay, so push and pop is the default one.
Yeah, you will use STMDB. Everything.
Yeah, this one.
You will use STMDB.
Unless I want to ask you what happens when you have STMIA, for example, just for the fun of it, right? In the test, I say, okay, I'm using STMIA. What happens? So then you must know lah. There are two different styles of stack. But to be simple, everything is push and pop lah. Li Ji Shuang say, is the instruction set will be provided inside test one appendix? Sure, why not? I can provide that. Just remind me. After all, the test is going to be online. So if I forget to provide you, just tell me, just straight away upload for you one, no problem. But the list is very compact. It's not, let me try to find that. Okay, just 1 second. Let me just stop sharing for a while.